Good morning.
Okay, good morning everyone. Welcome to our webinar here for phytoremediation with energy crops for biofuel production, for clean biofuel production, I should add. So, as you would have seen on the invite, we're going to hear from 3 different projects this morning: Gold, Phytoclimate and CERESiS. These are all projects financed by the European Union under the Horizon 2020 programme. They all have the same goal, and I'm going to present that to you in 1 second. We'll just wait for a few more participants to enter. Whilst we're waiting for the participants to enter in the room, I'll just give a quick reminder of the housekeeping rules. So as a participant, you won't have the ability to talk, but you can ask questions and also answer them, but we encourage you to ask questions in the questions and answer box that you'll find at the bottom of your screen next to the chat box. In the chat box, we'd like to reserve that only for technical questions or just hello, hi, I'm here. I mean technical questions as in I can't hear you, or can you, I can't see the screen, that kind of technical question. If it's a technical question related to the subject, please ask it in the questions and answer box. Now, for the agenda today, we're going to hear from the 3 projects, and then we're going to have a discussion. So we'd like to reserve any bigger discussion questions for the end. So if you write your question and it's not responded to straight away, please wait until the second part of the webinar. Okay, so I think we've reached lots of, I'm just looking at the participant numbers. So I'm going to go over now to the introduction. And share my screen. Okay, so here we are again. Well, this is the webinar. Here are your presenters today. So we'll have Eleni from Gold, Alfreda from Phytoclimate, Richard from CERESiS, and Marcus is going to be our overall moderator and chair for the whole presentation, and then at the end for the discussion. So let's begin. So why are we here? Why are these 3 projects here together? In 2020 or end of 2019, these 3 projects started writing proposals for the same call. And this is the call: building a low carbon, climate resilient future, secure, clean and efficient energy. So with the same similar goal, similar idea, all 3 projects wrote their proposals, not knowing about each other. And then at the end, these are the 3 winning projects that received funding for this combined clean biofuel production and phytoremediation solutions for contaminated lands worldwide. So what does that mean? What's the challenge here? So some of you might be coming from a remediation background, some of you might be coming from a biofuel, bioproduction, biomass production background. So in these projects, the biggest challenge is bridging the gap between phytoremediation strategies and clean biofuel production. So as you can see here, this particular call and proposals were dedicated to biofuel production at large scale, but without putting risk to land use change. So there was lots of parts of this that makes it very difficult to come up with a solution. But these 3 projects are working towards this. We call it bridging the gap. So how can we grow biomass on contaminated lands and then turn it into biofuel? And as you can understand, this is a really low risk to change in land use. So the scope really is to optimize energy crops with phytoremediation by targeting different classes of known soil pollutants and integrate it in the conversion process to biofuels. It's complex and there's lots going on. And so the type of plants that biomass plants was going to be spoken about in the presentations coming up. But this is just about the scope. So the scope was that pilot scale small trials were requested. International cooperation is encouraged. So you'll see and you'll hear from our other project presentations about our international collaborations all around the world. At the end of the project, at the end of the research, we were looking for TRL 4 to 5, so it's low TRL. And all of these projects have received funding from the EU of between 2 to 4 million. So I think we can all agree it's a win-win situation because we're bringing polluted land back to agricultural production and all on low risk iLUC lands. So other things we're looking for is cost reduction and improved phytoremediation. That's what we're going to be hearing about today. All of these projects have a substantial contribution to the Sustainable Development Goals set by the UN. We're contributing towards clean energy production and also international cooperation. So the process, very simply, for all of these 3 projects is very similar. So it starts with the crop and site selection, then onto the field trials, obviously the harvesting, then the conversion process, and then an assessment and recommendations for policy and other future, what could we say, making this the future of this type of technology. So in this webinar, we're going to hear about the first 3 points there, about the crop selection, the field trials and the harvesting. Our projects are at different points. So it will be varied, the amount of results and the amount of information you're going to hear, but overall you'll understand about this part, the phytoremediation part of the project. But just so that you're not left a bit confused, I'm just going to quickly run through the conversions techniques that they're all going to use. So after the biomass crops are harvested, these are some of the routes. Well, these are all the routes that our projects are using. I won't read it all through here, but gold is looking at using 2 different conversion routes. One is a high temperature entrained flow gasification, and the other is autothermal biomass pyrolysis. Phytoclimate is applying a biorefinery process based on thermocatalytic reactions consisting of a synergistic combination of technologies. Okay, and CERESiS is researching 2 thermochemical processes, one being supercritical water gasification and the other with Fischer tropics upgrading and fast pyrolysis. So these conversion processes will be covered in another webinar much further along the line, probably this time next year. But today we're just going to be focusing on this first step. So the first step of bridging the gap. So we're going to look at which crops were determined as being the best to grow on contaminated soils to yield the biggest feedstock for our liquid biofuels, and how it went. So any of the results from the first, or like I said, some of these projects have more than 1 year's results. Others are just in the first year. So we're going to hear from all 3 projects today. And now I'm going to hand over to Marcus, who's going to be the moderator and the chair for these 3 projects.
Thank you, Emma. Good morning from my side. My name is Markus Buschenreiter. I'm working at the University of Vienna Institute of Soil Research. And since I have been involved in several national and European projects on phytoremediation, I was asked to moderate these presentations and the subsequent discussion in this webinar. And as Emma said, we will get now an introduction of the 3 European projects that work on the target of phytoremediation combined with clean energy crop production. And the first presentation will be given by Eleni Papasoglu, presenting the GOLD project. Eleni, I would like to ask you to share a screen and to present the GOLD project. Thank you.
Thank you very much. Do you see my screen?
Not yet.
Not yet. Okay. Now?
Yes, you have to switch to the presenter mode and then it's...
Yes.
To the presentation mode, sorry, and then it's fine.
It takes some time. Okay, now?
Yes, now it's fine. The floor
Okay.
is yours.
Okay, thank you very much, Marcus. This is an excellent opportunity to share our very first results from our GOLD project. My name is Eleni Papasoglu, and I'm an agricultural engineer working at the Agricultural University of Athens. And my main field of expertise is phytoremediation. I have participated also in several European projects, and I'm very pleased to be a partner in the GOLD project. First of all, I would like to ask you to apologize for my voice, but I have a flu, so please forgive me for that. And now I will start to present our project. We have established 5 experimental fields in Europe and 2 in Asia. In Asia, we have 2 Chinese partners, the Institute of Bast Fiber Crops and the Hunan University. They are both colleagues attend this webinar. At the beginning, I would like to discuss a little bit the situation in China. They have proceeded with their pot experiments, but unfortunately, they had some problems with the establishment of their field experiments because there was a delay due to COVID situation and restrictions, as all of us knows very well. And when they sowed the seeds or transplanted the rhizomes, a huge flood followed and then a very dry season, so they failed. And this year they are going to re-establish their experiments. So mainly in my presentation, I will focus on the field experiments in Europe. So as a first indication, I would like to let you know that we are working with 4 energy crops, which were selected from the beginning. We are working with 2 perennials, and more specifically with miscanthus and switchgrass, and with 2 annuals, with sorghum and industrial hemp. We decided to work with these crops from the very beginning because they are high yielding and fast growing. They have relatively low input requirements, and we know from our previous experiences that they are relatively tolerant to heavy metals and metalloids, and they have the ability to grow in contaminated sites. In addition, we decided to test 3 biostimulants in order to optimize the phytoremediation strategies. That means to to increase the potential of our crops to uptake the contaminants. And these biostimulants are protein hydrolysates, fulvic and humic acids, and mycorrhizae. And we decided to work finally with 5 treatments, each biostimulant separately, but also their combination, as you can see here. So we have only protein hydrolysates, only amino acids, only mycorrhiza, and combination of them with mycorrhiza. Of course, against the control. At this point, I would like to say something about switchgrass. Unfortunately, we could not find on time seeds of switchgrass. It was a quite difficult procedure, even though we tried a lot, searching over the world. So finally, in our pot experiments that you will see in the next slides, we failed to cultivate, to produce, to grow switchgrass, and for this reason, in our field experiments, we replaced switchgrass with sorghum. However, CERESiS, in our experiment in the northern part of Greece, established switchgrass. I will show you some results later, but it is the only partner who could do that. And this year, we are going to establish this crop in our fields. So, as a first step, we decided to accomplish a pot experiment because we had, as you can understand, 6 treatments, 4 crops. If we were going to also to use 3 replications, it was going to be a huge experiment and difficult to be maintained. For this reason, we decided as a first step to test our treatments in a pot experiment in our premises, and then to select the 2 best performed treatments that will be applied in the fields. So initially, we collected soil from our fields. As you can see here in these pictures, we transported the soil to our premises. We filled our pots. Finally, we have 76 pots. We sow our crops. We have passed a huge difficulties with switchgrass, as I told you before, but finally, we managed to have some good results. Here you can see some pictures from our pot experiments, and again here from Maua and CERESiS. And this is a table in which I am presenting you the conclusion of the pot experiment. As you can see, the best performed treatment was amino acids and mycorrhiza, this combination. So we decided, all the partners involved in Work Package 1, to this treatment to be a common treatment for all the fields. Of course, we had the control, all of us, and each one of each partner, according to the results of the pot experiment, applied in the field a different treatment, also according to the crop. For example, in Italy, as you can see, for miscanthus, the best treatment was the amino acids, while for industrial hemp, it was the protein hydrolysates. And so these were applied to the fields. Again, in China, just a quick note that because it is forbidden to cultivate industrial hemp in fields, we decided that this crop should be replaced with kenaf. And now let's have a look in our fields. First of all, I would like to say that in Greece we have 2 fields where we have established our experiments. The first site is in Lavreotiki. It is 60 kilometers southeast of Athens. This is a long-term and multi-metal contaminated site. It is, I think, the worst site. This is a picture from our field. We have an ancient and more recent mining and metallurgical activities that resulted in a heavily burden of the soil. The main contaminants are lead, zinc, cadmium, nickel, arsenic, and antimony. Here you can see the results from the analysis of soil from our field. As you can see, you have extremely high concentrations for lead, 8,700, up to 600 for zinc, 6,000, sorry, for zinc, 21 for cadmium. Nickel is not so high comparing to the others, but nickel is geogenic in our case and not anthropogenic. Also, we have increased arsenic concentrations and antimony. And here with yellow, I have put, just to give you an idea, how many times higher than the common values are the contamination in our field, according to Kabada-PDS. This is a picture from our field, and this is the experimental layout. So some pictures, these were taken in July, I think, anyway, this is hemp, a picture of hemp. And as you can see, our crops are very thin. They have very thin stems. What was amazing for us, it was that the first 2 months, both hemp and sorghum were growing very well, but then their growth stopped. The hemp, the stems remained thin, and also they completed their life cycle very quickly. That means that we had plants either of 50 centimeters height, but they produced panicles, and the same was observed in sorghum. These plants are 4 months old already, and please remember this picture. My height is 1.70 meters, and I will show you another picture in the next slide from the other experiment in the northern part of Greece to compare the growth of sorghum. It is the same variety, of course. And this is miscanthus. We harvested miscanthus this January. And of course, we observed some phytotoxicity symptoms in both hemp and the sorghum. These are the results from our yields. As you can see, they did not differ significantly. The treated crops, the treated plants between the when compared to the controls for both crops. Sorghum, in our case, reached 12.5 tons per hectare, but hemp was only 1.6 tons per hectare. And these are some very preliminary results, initial measurements we have accomplished before harvest the crops. We just collected some crops from the field, and we have sent them to our Polish partners to measure the heavy metal and metalloid concentrations in the plant tissues, because we wanted to be sure that finally we will have a contaminated biomass. As you can see, both hemp and sorghum, and for all treatments, collected, concentrated all the metals, but in concentrations much higher than the normal values. We can say that both crops concentrated lead, sorghum concentrated zinc, and cadmium. So let's have a look now in our experiment in the southern part of Greece, in Kozani. This is a lignite mining area. The main pollutant is nickel. As you can see here, here are the results from soil analysis from 9 sampling points. And you can see that mainly the contamination is with nickel. Here are some pictures. This is sorghum, miscanthus, and switchgrass, and this is the 22nd of October. Again, our field there. This experiment was accomplished by Kres with Mete, and this is the picture I mentioned before. Again, me, I'm standing here, and this is sorghum. In that case, as you can see, it is more than double my height, and also miscanthus, it's higher. It's almost 2 meters high. And here are the results, the production of the experiment in Kozani. And as you can see, the switchgrass productivity was 7.6 tons per hectare, dry matter always. And this is a rather good production. And miscanthus reached the 9 tons per hectare, and the sorghum the 26.6 tons per hectare. And as you can see again, we don't have statistically significant differences among the treated and untreated plots. This is the experimental field in Poland. The region is in the upper Silesia. The experimental field is this one marked with yellow. It is very close to metalliferous waste dump site, which is marked with red. The main contaminants are zinc, lead, cadmium, and arsenic. Again, we have extremely high concentrations, zinc up to 8,000 milligram per kilo of soil, lead about 2,300, cadmium 51 milligram per kilo, and arsenic 94 approximately milligram per kilo of soil. Here is the establishment of the field and the experimental layout. As you can see here, there are two pictures from the field. As you can see, the plants are growing very well. They are healthy and very well developed. And these are some results from this experiment. The best performed treatment was B2, that is the amino acids. The production of fresh weight for hemp, it was 42 tons of fresh weight or 8 tons of dry weight per hectare, while for sorghum, again, the same treatment was the best performed, and the production was 115 tons of fresh weight per hectare and 20 tons of dry weight per hectare. The heavy metal concentrations are still under process. This is the experimental field in Italy. It is the site Chiarini 2 in the surroundings of Bologna. This is a part of an illegal dump field, Chiarini 1. The main contaminants, as you can see, is lead, copper, nickel, zinc, and tin. Here are the legal thresholds according to the Italian law. And as you can see, we have higher concentrations in soil. Here are some pictures from the field. The cultivation was sorghum, hemp, and miscanthus. And again, some more pictures. As you can see here, we have some phytotoxicity symptoms. In that case, we, apart from the inorganics in the soil, we have also organic contamination and more specific PCBs, but the analysis are in process. Also the analysis of the concentrations of metals in the plant tissues. And here are the results of hemp and sorghum productivity, dry biomass always. So for hemp, we have 30, the highest biomass was 33.8 tons per hectare, while for sorghum, it was 17.6 tons per hectare. As you can see, in hemp, we do not have statistically significant differences among the treated and the control plots, but in sorghum, the treated plots produces higher, significantly higher dry biomass than the control. And last, we have our site in France. It is the site Metal Europe Nord. It is close to Lille in the northern part of France. This is a picture from our field there. And the main contaminant is cadmium, lead, and zinc. As you can see here, they are in concentration higher than the common values. And this is a picture of the hemp plots during our meeting, which was accomplished last November. And this is another picture from the field trials. As you can see, sorghum reached the almost 14 tons per hectare of dry biomass, but we did not have, again, significantly differences between the treated and the control plants. And this is hemp. It was very well developed. The productivity was about 11 tons per hectare of dry biomass. But in that case, we had a failure of miscanthus because just after transplantation, a huge drought period occurred, and the plants could not grow very well. So we will re-establish the miscanthus this year in the field. And in France, we have also some results concerning the concentration of metals in the plant tissues. As you can see, both sorghum and hemp could uptake in levels higher than the limits of the ICP, but sorghum could concentrate cadmium in levels higher than the normal values, and hemp could concentrate lead in higher levels in the plant tissues for all treatments. And this is a summary table where we can see the best yield, always talking about dry matter tons per hectare, per plant and per partner. For hemp, the best yield was performed in Italy, and the worst in our field, in Greece, in the agricultural universities field. As I show you, the plants were very small. Also sorghum, in sorghum we had the worst production, but in that case I have to say that our field was also an extremely contaminated site. So the best sorghum was produced in the northern part, in the Cress field, and we have only one result from switchgrass, from Cress, as I presented before. And with that, I'm finishing my presentation. Thank you very much for your attention.
Thank you very much, Eleni. Regarding the discussion, I would like to announce that you can, during the presentation, you can ask your questions in the questions and answer box. And the general idea is that we now get the overview on the 3 projects, and then we will start the discussion. And I will take some of the questions that are posted in the question and answer box also as a starting point for the discussion. But I would also like to ask the presenters and other colleagues from the corresponding projects to maybe answer some of the shorter questions also directly in the questions and answer box, so that we can already provide some answers during the presentations. And then I would like to take some of these main questions as a starting point for the general discussion. Okay, so thank you, Eleni. And now I would like to ask the next speaker, who is Alfreda Casioliene from BioVala, and she will present the phytoclimate project. So please, Alfreda, you can share your presentation and start presenting your overview.
Yes, thank you. I will go on the full screen. Let me know when you see it on the full.
Now it's fine.
It's fine.
It's in the presentation mode. Thank you.
Okay, so hello once again. My name is Alfreda Casioliene, and I represent a small and medium enterprise called BioVala. We are established in Lithuania and work with the projects related to environmental quality improvement. And here, together with partners from other countries, we work in phytoclimate project. And the phytoclimate approach is to combine the phytoremediation of contaminated sites in several regions all over the world, and combine it with innovative biomass processing technologies to produce clean drop-in biofuels for transportation sector, as well as biocoke as substitution for petroleum coke for metallurgical industry. And in total, the project consists of 7 work packages, but today I will focus on work package number 2 that deals with the phytoremediation part. So pretty often you will see the short abbreviation WIPI2, meaning that that I talk about the phytoremediation work package. So the main goal of WIPI2 is to design and perform phytoremediation pilots of the contaminated sites in 5 countries, namely Spain, Serbia, Lithuania, Argentina, and India. And the work package includes all activities related to phytoremediation, like experimental planning, site preparation, implementation, monitoring, harvesting, pretreatment, pelletizing of biomass, and finally decommissioning of the pilot site. The project has started in the beginning of 2021. So in 2021, we all performed pot experiments. I will briefly talk about it. And in 2022, we all started the pilot field trials. And unfortunately, due to some reasons, India is no longer in the project. So I will be talking only about the remaining 4 countries: Argentina, Serbia, Lithuania, and Spain. Work package 2 is a central work package in the entire project because it has essential input and information exchange with all other work packages throughout the duration of the project. And very briefly, what are the other packages? So work package 3 is responsible for biofuel production. Work package 4 is responsible for assessment of environmental and social sustainability. Number 5 for commercialization. Number 6 for legal aspects and expertise related to phytoremediation. Number 7 for dissemination. And if you are wondering, in case where's the work package number 1, that's the package responsible for the project management. And now I will move on to the 4 countries. I will give a short summary of the test sites, short characteristics on contamination, why we selected certain crops, and present results in a very brief manner. Spanish pilot site. Spanish pilot site is located in Tarragona in Catalonia region, and it's within an industrial park close to Mediterranean Sea. Sources of contamination are due to leakages in buried pipes due to accidental spills, and the main contaminants are total petroleum hydrocarbons, or PPH, I will use this abbreviation lately, polycyclic aromatic hydrocarbons, PAH, and some others. And there was a monitoring done in 2014, and the concentrations of TPH in soil were 2,500 milligrams per kilo in soil, and in groundwater about 30,000 micrograms per liter. So the site was divided into 4 blocks, as you can see in the picture. And then the initial characterization was carried out. This table here shows there was a high heterogeneity between the sampling points and the depths within the same sampling point. And the highest concentrations of TPH were found to be in the P4 block in the greatest depth, and it was more than 5,000 milligrams per kilo. This slide shows the progress of Spanish phytoremediation campaign within the project. So the phytoremediation strategy was designed from preliminary laboratory scale trials that lasted 5 months. The trials were carried out in pots under normal conditions. 4 different plant species were used, and as well as 4 different amendments. And according to the pot test results, the field trial was then implemented using a rotation of sorghum and Brassica napus species. Also amendments, namely PG, PR, or plant growth promoting rhizobacteria, plus compost plus biochar was also applied. And the year 22 was finished with the harvest campaign, and the first batch of pellets were shipped to the further biomass conversion experiments. And also in the end of 2022, the further sowing campaign for 2023 was restarted. The pot experiments showed that the concentration of TPH and pH rapidly decreased in all contaminated soil cases. This upper graph shows that TPH removal efficiency in all cases reached more than 90%, and most likely that the highest effect had soil microorganisms. The lower graph shows biomass production, and the highest production of biomass was obtained with sorghum and with the brassica species, and therefore they were selected for field trials. Also, nutritional deficiencies were observed. Yes, according to the pot test results, the sorghum and brassica napo species were sowed in the field. And after 3 months, it was observed that the specimens established in the control plots that are in the graph are indicated with letter C, were more luxuriant and all had panicles, and the average height was about 1.3 to 1.7 meters. And plants developed, plants that developed on the most polluted plots, E2 and E4, showed much worse development. The plants were very small, with average height only about 0.8 meters. The total concentration of TPH of the experimental parcels had been considerably reduced by the establishment of the phytoremediation technique. So the total TPH concentration, you can see here in the table in the last line, it was reduced very considerably. Also, pH showed concentration levels that were below the reference values. And in general, the most contaminated plots have achieved TPH removal up to 86% efficiency. And now last word about biomass output. Biomass production in the most contaminated plots, E2 and E4, is estimated to be approximately 72% lower than in the parcels established in control zone. And it is 24% less for the plots with medium contamination. And this picture on the left shows the post-harvest drying phase of the plants. So later these plants were milled and pelletized and sent to biomass conversion technologies. So now let's move to Lithuanian pilot site. I am from Lithuania, so this is the part that I know the best. So the site is located in northern Lithuania. It used to serve as a former oil base in Soviet times, but now everything is demolished. And a monitoring survey was carried out in 2014, and it showed that the soil is highly contaminated with BTX, or benzene toluene xylene mixtures, total petroleum hydrocarbons, heavy metals, and other contaminants. Sources of the contamination: careless petroleum handling, petroleum seepage, careless removal of oil tanks, and so on. And these two pictures show the progress. When we started working in the area, it was overgrown with shrubs and bushes and had a lot of demolition waste. So it was a lot of work to clear it out. So at the beginning, we divided area into 3 blocks, as seen in the picture. It was visually clear where the highest contamination was. Like when we were digging out soil for samples, we found dirty, oily soil like in this picture. The table here shows what concentrations of petroleum hydrocarbons, split in different fractions, were detected. And in majority of cases, it was above limit values. Other contaminants that I mentioned were higher than background values, but not exceeding the limit thresholds. So we here focus mainly on TPH. The pot experiments were carried out in greenhouse conditions. There were Jerusalem artichoke, amaranth, 3 different mixes of herbaceous plants. We also used mineral and organic fertilizers, as well as PGPR. And we didn't differentiate in different setups. We just used the amendments according to agricultural practices. And in this table, I show you what was the biomass output from pot experiments. Pay attention that the area is very small. It's basically the area, the surface area of the blue box. And we obtained this much of dry matter. And then we recalculated what could be the estimation of biomass output from 1 hectare. So basically what we should expect from the field trials. This slide shows the decrease of TPH in soil after pot tests. So the TPH is split into 4 fractions, and in all cases we can see that lighter fractions were degraded faster, while the heavier fractions remain persistent. And although the decrease in TPH was observed everywhere, it was not enough to reach permissible levels. But the pot experiment also helped us to identify which herbaceous plants are the most promising, and we used them in the field campaign in 2022. So basically the same setup, the same additives, and we also enlarged the area to ensure that we obtain enough dry biomass for further experiments. The middle picture shows the soil preparation, and you can see in the far back how the soil is dark. So the soil is dark not because it's wet, but because it's mixed with a lot of oil products, let us say. And then the last picture is already of Jerusalem artichoke blooming at the end of summer 2022. This slide shows, this table shows what biomass output we received after the first year. So the column says parcel area, what we had in the field, total biomass, what we obtained from that particular field. We recalculated to 1 hectare. And in the last column, I put what we estimated from the pot experiment. So you can see that the estimations were right only for herbaceous plants, while for Jerusalem artichoke and for amaranth, there was a lot of overestimation, and I will explain you later why. The pellets are what we made from herbaceous biomass, and that will be used for thermocatalytic reforming. After the phytoremediation trial, we exploited our soil once again, and we found some positive results that organic matter improved, electrical conductivity improved, there were more microbial biomass, total carbon and nitrogen also improved. On the other side, we found that pH slightly decreased and that the soil was depleted from phosphorus, potassium, and from magnesium. That needs to be addressed in the coming growing season. And the graph here shows the reduction of total petroleum hydrocarbons, and especially herbaceous plants were very effective. And although we cannot reach, we haven't reached the limit values, that is 200 milligrams per kilo for soils, but the results were very promising, and we hope to decrease the TPH concentration even more the next year. First conclusions from our pilot site. Well, we faced the overestimation of biomass output in the field scale. It was because we realized that we have poor quality of amaranth seeds that showed low germination. In the field, we planted Jerusalem artichoke according to agricultural techniques, so the planting density was lesser than in the greenhouse. We had weed problems. As I said, herbaceous plants demonstrated one of the best performances. What this picture shows on the right is that in the hotspots, plants didn't develop that well, and it needs to be addressed. And then 1 year cycle is insufficient to reach permissible values, and it's difficult to extrapolate how many years we would need. For this year, the herbaceous plants are perennial, so we don't need to reseed them. Jerusalem artichoke will sprout from tubers left in the ground, while amaranth needs reseeding. So these are the closest plants for Lithuanian pilot site. Now moving to Serbian pilot site. The area is located next to Begi Canal, that is partly in Romania, partly in Serbia. And the pilot site has a total area near to 4,000 square meters. And for the purpose of phytoclimate project, the site was divided into two sections, landfill 1 and landfill 2. And in 2017, some sediments were dredged and put into landfill 1, while landfill 2 was filled with sediments in 2021, if I'm not mistaken. And then the contaminants are typical to sediments: copper, chromium, lead, and zinc. Also high levels of pH and other cancerogens. This is the timeline of Serbian activities. So far, they did two pod testing trials, and we'll start the third one. And due to climatic conditions, their first growing season is already over, and they are halfway in the second field trial season. So Serbia mainly used rapeseed, and in pod test they selected as a prominent plant species already known from literature. And they wanted to test the efficiency with different PGPR products, and also to validate rapeseed's efficiency and compare to other energy crops such as sunflower, hemp, and white mustard. And although the sunflower, the SF column showed that the sunflower produced more biomass, but its phytoremediation abilities were weaker than for the rapeseed. So the rapeseed was selected for field trials. This table shows translocation factor, and practically everywhere it was lower than 1, and it indicates that the main mechanism of the metal removal so far has been phytostabilization and not phytoextraction, and this is due to low metal bioavailability, which was proven by sequential extraction. So the exchangeable fraction here is that black part which is barely visible in the graph. So that's the exchangeable part, which is very, very low. Yes, so based on the obtained result, the main challenge is to increase bioavailability of metals. Thus, the second set of pod tests was designated to increase bioavailability by using environmentally friendly acids like tartaric acid, glutamic, citric acid, and so on. I will not go into details of the methodology, but the upper graph shows there that after the usage of acidifying agents, the translocation factor increased significantly, and only rapeseed was used for the experiments. Growing season 1, I show it as a set of pictures with the time scale. We started from bushes and ended with a nice looking field with the yellow rapeseed. Yes, so I skipped a little bit, but first of all, the biomass output, it was obtained about 530 kilos of seeds and more than 2,500 kilograms of harvest residue. So we achieved the aim to obtain 40 kilograms of dry mass, and the crops were about 85% of the same yield as in comparison to the crop yield in clean soil production. There was no significant change in the total concentration of the heavy metals. This is shown by this graph, and the presented changes here are mostly due to heterogeneity of the pilot site. Although the translocation factor was significantly higher compared to the translocation factor obtained in the pod test. and this could be due to longer period of contact with contaminated soil. So the pilot sites, the field trials proved that potential of efficiently growing energy crops on highly polluted soil is feasible, and the seed yield is similar to yield produced on agricultural soil. The low translocation of heavy metals from shoots to seeds, so seeds can be used for biofuel production. And that rapeseed shows high tolerance to bioavailable cadmium, and other metals were strongly bonded to soil organic matter, thus the rapeseed did not absorb them. And there was no leaching of heavy metals into groundwater. Sorry, my computer is a little bit lagging, but I told everything what's important. And the final moment for the Serbian part is the current situation on both landfills where the rapeseed was seeded for the growing season number 2. And now a few more minutes for Argentinian pilot site. The location is in La Plata, San Juan province in Argentina. From early 80s, it was a gold mine. Now it's abandoned, but it's still the soil still contains high concentrations of arsenic and zinc and accompanying metals like copper and cadmium. And there is a community next to the site, so people live very closely to the highly contaminated area. So for this project, the Argentinian team proposed to evaluate the usage of native plants that grow in that contaminated area. Some of them don't even have the common English name. I put it in Latin. And because the regular pot tests, as we did in other countries, were not possible because these species are shrubs and they grow much longer. Other tests like acute exposure test, chronic exposure test, chronic exposure test with the amendments were performed. And it showed that acute exposure for seed germination was at the level of 75% of contaminated soil. Chronic exposure was when there were 10% of contaminated soil in the growing media. However, this effect was nicely reverted when dolomite and compost were used, because these amendments are of basic origin, and they increased the pH, thus reduced the bioavailability of metals. For the field trials, 2 plots with different contamination degree were selected, and the amendments were used. Irrigation system, fence was also installed. And because although these native shrubs are well adapted to high pollution, it was not enough to produce enough biomass for the project. So the team proposed to use quinoa plants in order to obtain the desired amount of dry biomass. And because the different climatic zones, the first yield was harvested only last month, so we don't have more results to present here for Argentina, only to show you some pictures. But nonetheless, the Argentinian team was very active in outreach activities. They have our first publication that was published in Chemosphere, and you can find more details. And they work very closely with the community living there, trying to educate them about the contamination risks. And they presented in Society of Environmental Toxicology and Chemistry, so doing a lot of outreach activities. And with that, I want to finish my presentation. Sorry that it took 5 more minutes than planned, but we all have obtained a lot of information, a lot of data, so it's difficult to push everything into a very short 20-minute presentation. Thank you once again.
Thank you, Alfreda, for this great overview on all the activities in the Phytoclimate project. And since the time is progressing, I would like to go ahead with the presentation of the next project, of the CERESiS project, which will be presented by Richard Lord. So I would like to ask you, Richard, to start sharing your presentation and to provide the overview on the CERESiS project. Thank you.
Good morning, everybody. Can you see my screen now?
Yes, it's already in the presentation mode.
Great.
You can go ahead.
I'm Richard Lord. I work at University of Strathclyde, and I'm presenting on behalf of the Work Package 2 partners listed below for the CERESiS project, which is contaminated land remediation through energy crops for soil improvement to liquid biofuel strategies. So the CERESiS project, our strategy is to use phytostabilization, and by that I mean more mechanical than chemical processes, and energy cropping using perennial grasses. And we see this as the way to answer this question, bridging the gap between phytoremediation and energy cropping, because we hope we can produce high biomass yield plants with low contaminant uptake, choosing energy crop species which will maximize energy production and minimize downstream issues, but also maximize offtake and beneficial use of the site. So the project overall is set up with these work packages. This is work package 2 I'm talking about today, which is the energy crops and phytoremediation field trials, which we produce contaminated biomass, which is then processed through the technological work package through using fast pyrolysis and alternatively supercritical water gasification and cleanup and Fischer-Tropsch conversion. And then the overall work package, the decision support system, looks at the benefits and different approaches. So how did we come up with this strategy? Well, it's based on the bioregen project, which I led in 2005 and 2010, looking at growing energy crops on brownfield sites. And the first graph on the left shows the cumulative growth for 3 different energy crop species: short rotation coppice, miscanthus, and reed canary grass. And you can see that the reed canary grass at the top was something like 2 orders of magnitude more biomass production than either miscanthus or willow on these trials on brownfield, non-agricultural land in northeast England. Now, in contrast, the uptake of contaminants was the reverse pattern, much higher concentrations of zinc, for example, in coppice compared to miscanthus and reed canary grass. But surprisingly, such is the difference in yield between the reed canary grass and the other species, that actually the reed canary grass gave the greatest removal of contaminants overall. So this is what I mean by finding the energy versus phytoremediation sweet spot, that the most potent phytoremediation species may not be the best overall for remediation, and certainly isn't for the point of view of producing a viable, usable, uncontaminated or slightly contaminated feedstock for biofuel production or the maximum amount of energy. Now, had we been able perhaps to cultivate those crops on more agriculturally suitable contaminated land, then we might have got something like these results. If we achieve the yields typical for the UK, then for those contamination levels in the bioregen material, we would have got slightly higher offtake of contaminants by willow and miscanthus. But you can see from the scale, these are in grams per hectare per annum, so they're really not particularly significant in terms of the overall levels of contamination of these sites. So that's been the basis of our approach, to go for higher biomass productivity and lower contaminant uptake. And the partners who were involved in this work package: University of Strathclyde in Scotland, Renewable Energy Agency in Ukraine, Tisha University in Viterbo in Italy, and the Federal University of Guyana in Goiás. And here are some pictures of the different trials that have been taking place in these 4 countries. So which energy crop species have we chosen? Well, this is the list, and the ones in bold are the ones we've planted during the project. and the ones in grey are the ones where we've been able to use existing phytoremediation trials to harvest and assess the properties of those for conversion. So turning to each country in turn, first of all, the Brazilian sites, there are 3 field trial sites, and then the 4th is the laboratory where pot trials have been done. And the first site is Annikens in the top. You can see that this is a field site where there was a tannery which has contaminated the soil with chromium. The second site, Hydrolandia, in the middle at the bottom, is a military site which is contaminated again with chromium and nickel through explosives use by the military. And then finally, the Chrominia site, also with chromium and nickel. Contamination is actually a mining site. So this is the main issue in this area, is the contamination of soils with chromium from manufacture of chrome products for tannery use, and then application of tannery effluents to agricultural land. So the Brazilian trial species we're using are capiaçu grass and napier grass, 2 varieties of pennisetum, and also sugarcane, both energy cane and the proper energy sugar cane itself. And here's a picture of the field trial at Annikens in Brazil. And we have some initial results from all the field trials actually in Brazil, but I've just chosen this one to illustrate this point, that we have fairly low uptake of chromium in the biomass compared to the chromium levels in the soil. So maybe 2% levels in the biomass compared to those in the soil. And the biomass productivity is greatest for the 2 varieties of pennisetum. Elephant grass is the local name for Uganda grass or napier grass. Elephant grass is also used for miscanthus in the UK, so it's slightly confusing, that name. But you can see that the biomass productivity basically controls the amount of chromium that's extracted from the soil. So turning to the Ukrainian trial sites now, the 2 sites were adjacent, part of an old Soviet farm complex in the area west of Kiev in Zhytomyr region. They were known to contain both fuel spills from refueling agricultural equipment, but also pesticide spills in the soil from the pesticide storage and equipment that was recharged there. So including things like lindane, the hexachlorohexane isomers, and then also compounds of mercury, tin, chromium, cobalt from pesticide use. So the Ukrainian partners were able to successfully establish both Recanera grass and miscanthus. There were issues in the first year actually with the establishment of Recanera grass, which required some irrigation. This is a dry site in particular, so that was replanted but then grew successfully once established. And that was the status at the end of 2021. Well, a year ago, you all know what happened. We held our breath and worried about war in Europe. And this site was particularly close to the line of the Russian invasion heading towards Kiev as well. So we hadn't put that in our risk assessment for the project. But luckily, the trial survived and the Ukrainian scientists were able to visit the site not only this year, but also at the end of last year and collect samples of biomass and analyze the yields and also the contamination. So here I've shown the latest pictures of the sites after their second year of growth, giving the mature yields of Recanera grass is about 5 oven-dried tons per hectare compared to miscanthus of 20. So miscanthus is giving a better yield in this climate, as you can see, and also as an indication of the contaminant uptake, the concentrations of antimony there. So sub part per million levels of antimony, indicating that the phyto exclusion has been successful, and we've managed to grow fairly uncontaminated biomass from these contaminated sites. Turning to the Italian partner sites, these are in Viterbo. This is actually part of the experimental farm for the University of Tuscia, and it's a geogenically contaminated area from volcanic soils with high levels of arsenic, also selenium, beryllium, vanadium, cobalt, tellurium, and lead. And in the experimental farm, there were 3 areas devoted to the CERESiS project. 2 were essentially for biomass production for the downstream processing trials. And then the third, the trial, was an area of replicated trials to try and grow Canary gas successfully in Italy, as this is a novel plant for this area and this climate. So looking at replicated trials with different amounts of nitrogen amendment, and also with and without trichoderma inoculation as protection for the contamination. Some more pictures of the Italian sites, the replicated trials on the left, and also the area is a productive area for hazelnut and vines, and these produce biomass co-products. So we looked at the contamination of the same contaminants in those woody biomasses, and then also some of the impacts from the agronomy of Canary grass using low impact, no-till or limited till approaches to avoid disturbance of contaminated soils, and what that did to the compaction. So there are quite a few results now from this experiment, and the ones at the top are from the replicated trials, where we also looked at the effects of double harvesting. So in the first year 2021 and the second year of growth 2022, the different plots were divided into subplots and then harvested once or twice, and the double harvesting was also at different times. So you can see the results cumulatively here for the double mowing. That includes the first and second mowing results for that year. So there wasn't much difference in the double mowing compared to the first mowing. However, there was a difference in yield moving to the second year, which is what you'd expect from Phalaris as a perennial crop establishing into its second year. So the yields bottom right for the biomass production plots was something around 4 or more oven-dried tons per hectare, so a reasonable biomass yield in spite of the dry climate. And then the initial results for the contamination of the plant material, you can see at the bottom left, the plant biomass was actually only very slightly contaminated with arsenic compared to the levels in the soil. So again, it's working successfully as a phyto excluder, but producing biomass productively in this climate for arsenic. So finally, turning to the UK trials, which I'm slightly more knowledgeable about. These were focused initially on mine sites, so former lead zinc mining. The first 2 sets of pictures are from a site in northeast England where we already had existing trials looking at replicated different amendments with individually planted Canary grass plants. As you can see, the relics of that there in the top pictures. And then we were interested in trying to establish Canary grass in a non-invasive planting approach, so using compost blanket surface applied. So the last thing we want to do is actually cultivate these very highly contaminated soils and produce further dispersion of those contaminants. You can see that we've got percent levels of lead and zinc in those mine sites and mine soils. So these are actually areas of tailings and mine spoil. We also adopted an even more contaminated site in Scotland on the right. You can see that we've got up to 10% combined lead and zinc metals in the tailings there in a completely phytotoxic mine soil. And again, we used a compost blanket on the surface, and in this case with biochar addition as well. Now, the final UK site was close to the COP26 venue in Glasgow and is a brownfield site, again with moderately high levels of contaminants of heavy metals, copper, chrome, arsenic, probably from timber treatment, and is essentially an artificial soil composed of demolition rubble. So we were pleased to be able to establish Reconera on that sort of substrate, even a non-agricultural soil, and not really a soil, it's a demolition waste. And on the right, you can see the Scottish site, which has had 1 year to establish successfully on the compost blanket. So we've just taken some initial results from the biomass at all of these sites, which we've just received the results earlier this week. But we also had some initial results of the biomass from the UK trial site, from the replicated trials of different amendments. And you can see those at the top there. And the levels are extremely high, levels of zinc and lead, copper, and also cadmium. And that's why we have taken this approach of phytostabilization and physical phytostabilization of the soils, contaminated soils, while still producing viable energy crops. So you can see that Reconera has this fine root system, which is binding the soil. This particular trial is vulnerable to sheet erosion, and we've observed this in the past. And again, this similar sort of event happened this winter after the establishment on the compost blanket. And you can see the pictures at the bottom show the binding effect of this fine root network, so successfully binding the soil. So the sheet flood event has exposed the roots, but they've preserved some of the soil, and the Reconera grass is a particularly tenacious plant in this sort of environment because it's a wetland plant. So do we have a new hyperaccumulator with those sorts of levels of potentially toxic elements in the Reconera grass? Well, we don't think so. We've done some XCT analysis of the contaminated biomass, both washed and unwashed samples, and you can see the bright colors here are high density or high X-ray density phases, and you can see the clusters of high absorbance bright colors near the ligules of the Reconera grass, and much of that is contamination, so surface contamination, which has been removed by washing. So in detail, you can see here there's another similar XCT image showing the concentration of very small, very contaminated particles around the ligules of the plant, and the density compares to ceresite, which is lead carbonate, which is the main mineral phase of lead in this trial site. So we're now looking at what proportion of the contamination is sufficient and can be removed by washing, and what is inherent in the biomass. But suffice to say, we've shown that the effect of growing biomass on highly contaminated soils is that you get highly contaminated biomass. And we think from the other results from Reconera, where it's essentially a phytoexcluder, that this is from dust and from soil splash, so either dust deposition from wind or from the local soil or from soil splash. So what do we know so far from the phytoremediation trials? First of all, we've shown that Phalaris is a viable high biomass, low contaminant uptake energy crop species, not only in England now, but also Scotland, which is important because Seathorn miscanthus struggles, can't really be grown in Scotland, and also Italy and Ukraine. So we've extended the range to drier regimes, but it has to be irrigated, as we'll see. So we've also been able to use minimal or no-till cultivation to maximize energy production and minimize downstream issues, by which I mean downstream processing issues for the biomass. However, we need to irrigate to establish Reconera in Italy or Ukraine. And We've also observed that Rican aerogast needs cultivation or effective mulching, or native grasses outcompete in our no-till surface blanket approach to establishment. But we've also shown that the plant has a generally low uptake, so phytoexcluder, hence low levels of arsenic in the geogenic arsenic contaminated soils in Italy. But then on the very highly contaminated and mobile unvegetated soils in the UK, in mine sites, we've seen the effects of cross-contamination from superficial dust, from wind-blown material or rain splatter. And then turning to Brazil, where the real winner has been the elephant grass, the Pinacetum, the two varieties that have outperformed energy cane and sugar cane, and have all shown low uptake of chromium compared to the chrome contaminated soils. So we've been able to demonstrate that we can produce low indirect land use change biomass from these very contaminated sites in a range of different climates, but it has essentially been phytomanagement, not really phytoremediation and remediation of the contamination issue. Thank you. So that's the end of my presentation.
Thanks, Richard. So now we have completed the session on getting an overview on the three main European projects we are dealing with now in this webinar. So we can now go ahead with the general discussion. And as you could perhaps see, there were already several questions posted in the question and answer box. Some of them already have been answered. But still, I would like to take some of these questions to start the discussion, if you don't mind. And the first aspect I would like to look at is the aspect of plant production, because the production of sufficient biomass is one crucial aspect of providing sufficient biomass for the biofuel production in the end. And so it determines on several site-related factors like soil conditions, climatic conditions. And in this context, I would like to take one question that was posted regarding irrigation management. So especially on sites into the Mediterranean climate, but due to climate change, also increasingly also in Central Europe, the biomass production might largely depend on water availability. So does someone of you would like to comment on irrigation as one crucial factor to achieve sufficient biomass, but also other important soil management or site management strategies like fertilization or stabilization of contaminants or pest management and so on? Who would like to give some comment or share some experience on these aspects?
I can start and share my opinion.
Yes.
I think that bioenergy plants should be considered as any other agricultural plants, except that they are grown on the contaminated land and it's extra value. But if we think about corn, wheat, rice production, of course, irrigation, pest control, and fertilization are of critical importance. If we don't give anything for poor soil, if we let it dry out, of course, nothing will grow.
Mm-hmm.
And if we talk about field trials, what we implemented here, it has a scientific approach as well. So, of course, we want to fulfill the experimental goals, and at least from phytoclimate, some pilot sites indeed had irrigation systems.
Mm-hmm.
But in real scale, nature takes care of rainfall.
Okay.
Can I add something?
Yes, please, Eleni.
When we speak about phytoremediation, we have to keep in mind that we are working with a bad quality of soil, not only unfertilized, but also including contaminants, which poses stress to the crops. So if we will not irrigate, we will not fertilize, or we will not help the crops to grow, then you can understand that the crops cannot overcome the abiotic stress that they receive from the contaminants. In our case, it is, as you know, it is a dry climate in Greece, and the precipitation during the growing period was only 30 millimeters. So we established a drip irrigation system and we irrigated the crops, and also we fertilized them, especially in the site of Lavrion, which was really heavily contaminated. Because you can imagine, if we are talking for phytomanagement, we want to, and we are using energy crop as in this project, we need biomass. And if we need biomass, we have to give something to the crops to help them to address the stresses, the abiotic stresses due to contaminants. So, in my opinion, we cannot really have a no input agriculture when we are talking for phytomanagement in contaminated sites. Thank you.
Okay, thanks, Eleni. Any further comment or experience on site management issues, irrigation, fertilization, contaminant stabilization?
So I'll just really comment on I showed some results from the bioregen project right at the start, where Recanary gas had outperformed miscanthus and short rotation coppice willow. Now those were completely unirrigated. Obviously this is Northeast England, not Mediterranean climate, but it's still actually an issue, water shortage in non-agricultural sites. So brownfield sites, they can't easily be prepared in the same way that you would prepare an agricultural site for, say, willow production in the UK, where you do subsoiling and deep ploughing. You'd be aware that you need a good depth of soil for water storage, so from the natural rainfall, and you just don't get that on non-agricultural sites. So that's one of the reasons why we chose Recanary gas, and we haven't irrigated our Recanary gas sites in the northeast, but we do know the northeast of England, but we do know that even in this climatic zone that the summer period is stressful for plants, and that's an issue particularly for these non-agricultural sites without good soil profiles and with very limited organic matter. So several of the speakers today have mentioned using compost, for example, as a waste product, which can successfully improve the water holding capacity. So there are ways around this. The irrigation could perhaps be used as a strategy to establish energy crops on contaminated land. I would say it's acceptable to use it initially as a sort of treatment stage to get crops to grow, and then once they're established, if they can survive, then they could be harvested without use of scarce water resources, ideally.
Thank you, Richard. Any further comment from the speakers? Or is there a question from the audience? I think Pietro Peroni raised his hand before. Do you have a question on this aspect? Yes.
Just a little comment about also the Italian experience of Unibo in the Gold project is that basically the total amount of heavy metals that we can extract from the field depends, it's proportional to the biomass that we produce. So if we decide to focus our attention on the total capacity of extract heavy metals from the soil, increasing as much as possible the biomass production can be useful, because the total amount, not the concentration in tissues, but I think the expected amount of heavy metals extracted from the soils depends on the biomass, but depends on some agronomic inputs such as irrigation or fertilization. If we decide to put our focus on the sustainable production of biomass, also economical talking, then the answer can be different. It's what the Professor Lord talked about phytomanagement, I think, instead of phytoextraction.
Thank you. Then Michael Severino also raised his hand. Please ask your question. Sorry, we cannot hear you. You're still muted.
Sorry.
Yes.
There a question about the Brazilian experiment about the use of bagasse in a power plant. Yes, usually sugarcane bagasse is used in sugar and the alcohol plants. But in our experiment, we are not analyzing for this destination of food production. We analysis for gasification and the fast pyrolysis up to now.
Okay, thank you. Any further comment or question on this aspect? If not, then I would like to go ahead on the next step in the process chain. There were some questions about harvesting and post-harvesting treatment of biomass, for example, on drying. Eleni or Alfreda, I think, already answered these questions in the question and answer box, but maybe can you again share experience on how to treat the biomass after harvesting? Drying of a large amount of biomass can be a challenge. So what is your experience on that? Eleni, do you want to start?
Okay, yes, thank you. Yes, that was a huge task to be addressed because we had to send the biomass to our other partners in Germany, Italy, and the Netherlands. So as you very well know, if the biomass is fresh, it cannot be transported because it will be destroyed due to it will be rotten. So we had to dry the biomass. So we have sent the biomass to the facilities of CRES, where they have a huge oven like a room, and we totally dried the biomass so as to have also the dry yield, but also to be able to transfer the biomass to our partners. Because in another project, we collected the biomass, we left it here at our laboratory for 3 days, so as to have the time, you know, to find the oven, how to dry, and the biomass was rotten. So we had to start from the beginning. For this reason, we totally dried the biomass. Of course, that is a huge problem when we are talking for a real situation, a real phytomanagement situation. If we want to exploit the biomass for energy purposes, this is a serious issue, how to manage the biomass before transporting. Yeah, and that's why the conversion plants should be close to the agricultural land or to the contaminated land. Otherwise, they have to face this huge problem.
Thank you, Eleni. Richard, do you want to add something on that?
Yes, so one of the advantages of the supercritical water gasification is that we're using as one of our conversion processes is that it takes wet biomass. In fact, it's better to be wet. It needs to be a slurry, really. But we've had the same issue in terms of our project management that we've just heard about, that we had to dry our biomass samples from the UK so that we could grind them and stabilize them to then send them to Germany to KIT for the partner who are doing the supercritical water gasification step, who would then re-wet them as a slurry to process them in their conversion. So there are technologies, supercritical water gasification, for example, which can take wet biomass from the field for the full deployment of these technologies, but it's certainly a headache for the experimental stage.
Thanks, Richard. Alfreda, you also would like to add something?
Yes, I totally agree what Eleni said about the drying of biomass. We in the phytoclimate project, each pilot site had to, produce 40 kilograms of dry biomass. And 40 kilograms of dry biomass doesn't seem that much, especially when it's already milled and pelletized. But as a loose material, it's really a lot of, and we all had to plan ahead where to find warehouses, how to dry it, because This issue is important not only because the material will rot, which of course it will if not taken care, but some technologies like thermocatalytic reforming requires pellets, and pellets can only be made when the biomass is like 15% wet or has 15% of moisture. So the drying issue is of critical importance. And if we talk about even larger scales, bigger fields, so we will have more biomass that needs to be taken care of. For example, herbaceous plants can dry on the field and turn into a hay, but not every biomass will dry completely on the field. So it's an important issue.
Thank you. Any further comment or experience on the issue of treating the biomass after harvesting? If not, I would like to raise or take some questions from the question and answer box concerning the fate of the pollutants where the plants are growing. So all the sites that were presented contained either metal pollutants or organic pollutants or both. And concerning metal pollutants, there is some risk of transfer into the biomass, although the plants, most of the plants that you were using are excluders, but still some concentration limits might be exceeded. And the question is, or some of the questions that were raised were addressing the question, is it a problem concerning the processing of the biomass? Where do the metals end up? Do they end up in the ash or in the biofuel product? So what could you comment on the potential risk of metal transfer from the site to the biomass and to the final biofuel product? Who would like to give some comment on that? If it is an issue or not, or if the process is affected. Yes, Richard?
Yeah, so this is something which the rest of the partners in CERESiS are looking at in detail. So we've, although as I said, we've in the phytoremediation work package, we've taken our strategy as trying to produce as much uncontaminated or limited contaminated biomass by growing phyto excluders. The presumption from the downstream processing partners is that they will be dealing with contaminated biomass and will have issues which with PTEs which will particularly downstream will poison catalysts in the Fischer-Tropsch processes which are used for converting syngas into liquid biofuels. So they're looking at various ways of extracting these at different stages in the chemical processing. In the supercritical water gasification, there's a solid phase which settles out as a salt from the brine, and then the gas is actually what is used for synthesis. And the same for the fast pyrolysis conversion stage. We expect there the contaminants will be accumulated in the char. So we're then going to look at how contaminated that biochar is and whether it could be reused as a soil amendment on the contaminated sites or not. So it could be perhaps cycled back to in a closed loop to the phyto extraction, phytoremediation sites. But it certainly, the presumption is that the biomass contamination, even though it's low levels, will still be an issue. As we've seen in the UK mine site trials, but perhaps unsurprisingly, if you grow plants, even phyto-excluders, on highly contaminated bare soils, you will get a lot of contamination just from surface contamination.
Thank you, Richard. Any further comment on this aspect? Yes, Eleni.
Well, this is the most common question whenever we talk about the phytoremediation. Always when we present something in a conference or wherever, the question is about the fate of contaminants. So we had again the same issue here. But this is what we are trying to find within this project, to concentrate the contaminants, to collect the contaminants in a concentrated form. Of course, there is always the risk to release the contaminants through emissions or in the ash or in the char or whatever. But that is what we are trying to find out with this project. Because one of the main issues of the project was to concentrate the contaminants, to collect the contaminants in the concentrated form. So please be a little patient. Perhaps next year we will have better results. And at this point, I would like to clarify that our project started later than the other two projects. So we are in initial stage. We have just sent the biomass to our partners, so we don't have more results. Hopefully next year we will be able to give you more information about this very important issue too. Thank you.
Yeah, thanks, Eleni. Any further comment?
Yes.
If not, sorry, yes.
Sorry.
Yes,
in
yes.
addition, I can give a short comment that we also just pretty recently sent the biomass to thermocatalytic reforming, and we are not sure how the metals behave in that type of system. But I think that everyone here would agree that the majority of literature studies say that heavy metals usually don't end up in the intermediate products; they end up in the ash. So the biofuel production, for example, shouldn't be affected by metals in the biomass. Thank you.
Mm-hmm. Thanks, Alfreda, for this comment. Any further experience or yes, Emma?
I have a question about the soil quality, because although I'm dissemination communication, I actually am a soil specialist from a previous life. So Richard mentioned that we're not remediating, we're managing the contaminants. So I just wondered, so that's from the UK sites or all of the sites at CERESiS, and I wondered from the other projects, what's the outcome from the first year's worth of crop growing of the soil quality? Have we seen any marked improvements or small improvements or no change?
I can start from what we saw in Lithuanian pilot site. The soil quality indeed improved, but one of the most important reasons why it improved, because we gave some materials to the soil. We fertilized it, added compost, we added bacteria. So we gave a boost to the soil to be able to improve. And I showed in my presentation, especially in the Lithuanian part, that there were parameters that improved, but also when the plants were growing, they depleted the soil for certain nutrients. So if we want further on to increase the quality, we still need to to help the nature, the soil.
Okay, so there's an importance of the additives as well as
I would also call it a phyto management.
Okay, I like it. I like this title.
Yeah, thanks, Emma, for raising this issue. I also wanted to draw your attention on the aspect of soil quality, pollutant bioavailability in phytoremediation approaches. So yeah, thanks, Alfreda, for giving some, sharing some of your experiences. And I think Richard would also like to add something on that, and then next, Eleni.
Yeah, so I think if you're strict about phytoremediation, it means remedying the contamination. In other words, rendering soils suitable for future use, whatever that is. Although we also use phytoremediation as a general term to include all other types of beneficial effects of growing plants, so phytostabilization, rhizofiltration, and so on. so that's really what I meant, that we probably ought to be a bit careful about using phytoremediation in general, because it's for most of the contaminated sites we've seen. I suspect that if we work out the annual removal rates there, it's going to be decades or centuries before they're remediated and the levels are back to normal or acceptable levels. So in the meanwhile, we can phytomanage those. We can clearly show benefits from plant growth, establishment, and the economic benefits of having a productive use mean that the sites can have these soil amendments and waste products added to them, and to improve the soils for both ecosystem services and for reducing the environmental impacts of them, rather than just leaving them to be derelict. So it's a way of producing an income, we hope, for if not remedying the sites, certainly moving them in the right direction with a load of other environmental benefits and societal benefits at the same time.
Yeah, thanks, Richard. Eleni?
Yes. First of all, I would like to make a clarification that when we are talking about phytomanagement, we are talking about the cases that we use crops with an added value, and that they can give an additional income to the farmers. And I would like to ask from our partner Nadège Oustier, because they have done some analysis in the soil and they saw some good results, to give us some information about the case in France. Nadège, please.
Hello, everyone. In France, what we measure that the first thing we are talking about when we are talking about phytomanagement is first the decrease of the spreading of the contaminant in the surrounding environment. And so what we are trying to reach out is a decrease of the availability of the contaminant. And actually what we measured is that after only 1 year of yield, the availability decreased quite well in our field. Aside of that, we were also studying the function of the soil and how we can measure ecosystem services in the soil. And we also realized that some ecosystem services were coming back in our field. So even though we are not decreasing the total concentration of trace elements in the soil, we were able to bring back some soil function, and for example, we were able to improve the biodiversity in our hemp field. Thank you.
Thanks, Nadège, for providing some overview how the effect on soil quality can be assessed and which effects you already found after one growing season. Is there any further comment, or is there any further experience you would like to share on aspects of soil quality improvement? Yes, Snezhana, please.
Thank you. So I'm Snezhana Maletic from Serbian pilot site. So on opposite for French, we have problem with the bioavailability because our soil is actually clayey. So most of the metals are strongly bonded. And since we have a task to obtain translocation factor above 1, so we are struggling to a little bit increase, not too much, but a little bit increased that we don't have leaching, but to have some amount which plants can absorb. So we, Alfredo, show our pot test with acidified amendments, and for example, we choose to use acid fertilizers like ammonium sulfate to actually increase bioavailable fraction of some metals that they can be actually extracted from the soil. So regarding the soil quality, we didn't add, for example, some organic material, since this is actually Serbian site is aquatic sediments, which was rich in organic matter. So like 10% of organic matter, it's already there. So we didn't need to increase here. And the soil quality didn't change during this first season. So it remained the same, but we, as all of most of you did, we add fertilizers, we control pests, we control weeds, so we managed these sites to actually achieve a good production of the biomass. So thank you.
Thanks a lot. Before giving the word to Brian, I would like to ask you, so is the aim now to fight to extract the metals on your side? Because you mentioned measures to increase bioavailability. So the target is then really to remove the metals from the site. Mm-hmm.
Yes, mm-hmm. but it is, as we all know, it's a slow process. So we cannot achieve it like in 1 year. It will be a little by little. So, but the good result is that we didn't observe any phytotoxicity on our plants. So we have a yield similar to the usual agricultural production site. So it was on the same level. And on this way, so the aim is to increase, to extract metals, but in these available actually metals to extract from the soil.
Thank you. Brian, you would like to add something?
Yes, in our case, it's a Argentinian pilot site. In our region that we are working, soils had low quality in terms of organic matter, nutrients, and it has a high concentration of several metals and metalloids. For example, the pH is near to 2 or 3, depending on the zone. So we needed to add dolomite to up the values of pH. So the bioavailability of metals was lower with this change of pH value. Also we added compost in order to increase the organic matter content and nutrients too. And so it was allowed to grow the different species that we planted there, both native species, quinoa crop. So in this case, we needed to load the bioavailability of metals and metalloids, and it allowed to grow the different species.
Thank you, Brian. Any further comment on this aspect? In the question answer box, there was a question on the issue of potential economic incentives for using contaminated soil for some plant production or even for some removal of contaminants. Do you have any experience if such incentives exist in some countries or in some areas? Maybe it would be nice to have, but I guess it's not the case, but maybe you can comment on this question. Yeah, Alfreda.
At least in Lithuania, we don't have such incentives, and as far as I know, not in European Union. But we should start from the point where our governments acknowledge that there is a big problem where the large territories are contaminated with the low to moderate levels of contamination. And there are many sites like this. And we often pay attention to sites where the concentration of contaminants is very, very high and very acute effects to the surrounding. But usually we overlook those vast territories with lower concentrations of contaminants. And I think in the CERESiS and in Gold project, we deal with those lands. But the governments need to realize that this is a problem as well, and then to maybe start providing some incentives. But so far, it's not done. That is my opinion and my point of view.
Thank you, Alfreda. Alexandra, you would like to add something?
Yes, thank you. Just to add to what Alfreda said a little, yes, there are no incentives, but also there is a certain obstacle, as what we noticed, for example, with other sites, contaminated ones that had trees grown on them, acacia or robinia trees, and when there was an idea to cut and test the trees, it was prohibited. So another, it's like an obstacle. So we also need to work with this, to work with government on this, to allow harvesting or collecting biomass from low or medium contaminated sites for the purposes of producing clean biofuels with certain technologies. So this is also can be an obstacle, because governments and population can be afraid that if you collect contaminated biomass, then it can be, for example, burned and the ash can be blown around. So this also needs attention and further work in this direction as well. Thank you.
Thank you, Alexandra. Is there any further comment on the role of regulators or local or national authorities? Emma, you would like to add something, and then Richard?
Yeah, I just saw Richard's hands, but just quickly to add that all of these projects have a work package which is dealing with the policy and recommendations for the future. So that will be a future webinar. If our listeners stay tuned, that will be maybe next year or the year after.
Okay, yeah, Richard?
Well, I was just going to add to what Alexandra said, that the issue really is not there's an incentive, there's actually a disincentive, because if the biomass is contaminated, there's certainly a perception of risk from the users. And then the reality, if you test it compared to standards, if it didn't match, for example, the European EN standards for pelletized fuel, you could argue that it's a waste under EU regulations. So that it is a disincentive to do this. So you might expect to get lower yields as well on contaminated sites. So you're trying to do something which is more difficult, more expensive, and then gives you material which is less valuable. So there needs to be an incentive to balance those societal, environmental benefits from reusing this neglected indirect land use change type of resource. And usually for remediation, the incentive is the value of the restored or remediated land for redevelopment, which doesn't apply in this case. So yes, we do need some incentive to do this somehow, some policy intervention. Thank you, Richard. Alfreda?
Yeah, I just wanted to add a quick word on societal perception, as Alexandra said, and as Richard commented, that when people find out that the biomass might possibly have tiny concentrations of heavy metals, or they've been growing on oil polluted land, there is like a demon inside there that this biomass will be strongly contaminated. But what people don't realize, that burning fossil fuel, burning coal and oil, it actually it actually contains higher concentrations of heavy metals, and there are emissions that are actually higher than from biomass conversion technologies. So this perception really needs to change in order for the phytoremediation to progress. And and we also have a work package that deals with the social acceptability of phytoremediation, and they perform many surveys and questionnaires. So maybe there will be a time and place to present those results as well in the future. Thank you.
Yeah, thank you. Eleni, you would like to add something as well?
Yes, I totally agree with Alfreda and Richard and the rest. But we have to keep in our mind that also the agricultural land, a huge part of the agricultural land is slightly contaminated. And this is something that nobody wants to touch. For example, I'll give you an example from my side, which, as you have seen, it's heavily contaminated. But you have seen the field that I have. It is actually an agricultural land, which used to be cultivated for food production. And the neighbor from both sides are cultivating vegetables, which they are consumed, of course. And when they are asking us, is there a problem with the soil? And we say, yes, it is heavily contaminated and all this. They say, oh, come on. We are living here for so many years and we don't address any problem and so on. But the 36% of the children in the area have lead more than the threshold in their blood. And a lot of diseases are they are suffering from a lot of diseases. So this is a very sensitive issue that we are working with phytoremediation have to keep in our mind, how to convince people and how to address, because most of the time they are asking, what should I do? Should I leave my house and move to another area? What can you answer to that question? Yes? Well, it is difficult. Thank you.
Yeah, thank you, Eleni. It's 1 minute past 12, so we have already come to a conclusion, and I think what we discussed now finally is already going into a kind of conclusion or some perspective, also on a wider perspective on the importance of soil management, of contaminated soil management, and the use of such sites for crop production that can be used for biofuels, I think is a very important potential management option for such sites, and offers a lot of potentials, as we could see in the presentations and also what we could hear now in the discussion. So at this point, I would like to thank all the speakers and everyone who contributed now to the discussion. I think it was a great overview on what is going on in this 3 project and in the area of phytoremediation combined with biofuel production in general. I think it was a very exciting and interesting webinar. I don't know if Emma would also like to give some final words on concluding this webinar for today.
Yes, thank you, Marcus. I just wanted to say to thank all our participants, all the questions that came in from the audience, and just to let you know that the recording and the presentations will be available online under all the respective projects. And please stay tuned either through Gold, Phytoclimate or CERESiS for future webinars. Thank you.
Thank you all.
Thanks.
Okay,
Bye.
thank you.
Thank you very much.
Have a nice day. Bye-bye.
Thank you.
Bye-bye.
Bye.
Thank you.
Bye-bye,
Bye-bye.
Everybody.
Thank you. Bye.